Hi everyone, welcome to Paralton video lecture. Myself M.KRISHNA, working as assistant professor in Triple E department, St. Peter's Engineering College, Hyderabad. In this video, I am going to explain about dual converter. Dual converter is one in which it converts AC to DC and DC to AC at the same time. As the name suggests, dual converter has two converters. One converter works as a rectifier, another converter works as a inverter. The both converters are connected back to back with a common load. Why we use the dual converter? If only one converter can supply the load, then why we use the two converters? Here we have two converters connected back to back. Due to this type of connection, this device can be designed for 4-quadrant operation. It means that both load voltage and load current becomes reversible. Here 4-quadrant operation takes place in dual converter. First quadrant, voltage and current both positive. In the second quadrant, voltage is positive but the current is negative. In the third quadrant, voltage and current both are negative. Fourth quadrant, voltage is negative but the current is positive. We are able to see all these things in the quadrant operations. Out of those two converters, the first converter works in two quadrants depending upon the value of firing angle alpha. This converter works as a rectifier when the value of alpha is less than 90 degrees. In this operation, the converter produces a positive average load voltage and load current and operation in the first quadrant. When the value of alpha is greater than 90 degrees, this converter works as an inverter. In this operation, the converter produces negative average output voltage and the direction of current is not changed. That's why the load current remains positive. In the first quadrant operation, the energy is transferred from the source to the load, and in the fourth quadrant operation, the energy transferred from the load to source back. Similarly, the second converter operates as a rectifier when the firing angle alpha is less than the 90 degrees, and it operates as an inverter when firing angle alpha is greater than 90 degrees. It is exactly opposite to the first converter. And when this converter operates as a rectifier, the average output voltage and current both are negative, so it's operator in the third quadrant, and the power flow is from load to source instead of source to load. Here the motor or any other application is in rotating reverse direction. When this converter operates as an inverter, the average output voltage is positive and current is negative. So it is operate in the second quadrant and the power flow is from load to source. When power flow from load to source, the motor behaves like a generator, and this makes regenerative braking possible. The basic principle of dual converter will be explained with the help of ideal dual converter. Here in this we can able to see ideal converter. In the ideal converter, actually it is ripple free at the output terminals, and the converter operating as a rectifier is called a positive group converter, and the other converter working as an inverter is called as a negative group converter. The average output voltage is a function of the firing angle, and firing for single phase inverter and 3-phase inverters, the average output voltage are given below. Generally, this is a universally following the equation. EDC 1 is equal to Emax cos alpha 1, EDC 2 is equal to Emax cos alpha 2, where alpha 1 alpha 2 are the fire angles of converter 1 and converter 2 respectively. For single phase dual converter, the voltage value is maximum when we are taking 2 em upon pi. It is the value for 3 phase is different one. E max is equal to 3 root 3 em upon pi. And in case of ideal dual converter, this V01 is the output voltage from the first converter, V02 is the output voltage for the second converter, and it is from left side to right side the operation of converter 1, from right side to left side operation of inverter, that second converter. And we can able to see the some equations. Here the main equation is alpha 1 plus alpha 2 is equal to 180 degrees. And as we know, if alpha is less than 90 degrees, the operation is rectified. If alpha is greater than 90 degrees, we can say the operation is inverting. When we see the practical dual converter, it is necessary to control the circulating currents. There are two modes of controlling the circulating currents. They are operation without circulating current and operation with circulating current. We'll see first one, operation without circulating currents. That is, in this type of dual converter, only one converter is in induction and another converter is temporarily blocked. So at a time one converter operates and the reactor is not required between the converters. At a particular instant, let us say converter acts as a rectifier and supplying the load current. At this instant, converter 2 is blocked by removing the firing angle to converter 2. For inversion operation, converter 1 is blocked and converter 2 is supplying the load current. The pulses to the converter 2 are applied after a delay time. The delay time is normally around 10 to 20 milliseconds. Why we apply delay time between the change of operation? Because it ensures reliable operation of the thyristor. If converter 2 is triggered before the converter 1 is completely turned off, a large amount of circulating current will flow between converters. There are many controlling schemes to generate a firing angle for circulating current free operation of the dual converter. These controls schemes are designed to operate very sophisticated control schemes. Here, at a time, only one converter is in conduction, therefore it is possible to use only one firing angle unit. Some basic schemes are there to produce the firing angle. The converter selection by controlling signal polarity is important. Converter selection by load current polarity is also important. Converter selection by both control voltage and load current also important. We'll see the dual converter with circulating current mode operation. In without circulating current converter, it requires very sophisticated control system. The load current is not continuous. To overcome these difficulties, there is a dual converter which can operate with the circulating current mode. A current limiting reactor is designed with higher values, is connected between the DC terminals of both the converters. The firing angle of both converters is set in such a way that the minimum amount of circulating current flow through the reactor. The advantage of this scheme is that we can get smooth operation of the converter at the time of inversion. Time response of the scheme is very fast. The normal delayed period is 10 to 20 milliseconds. This is having disadvantage of the scheme is that the size and cost of the reactor is high. Now we'll see the single phase dual converter. The circuit diagram of the dual converter is shown in the figure. Here a separately excited DC motor is used as a load. The DC terminals of both the converters are connected with the terminals of the armature winding. Here two single phase full converters are connected back to back. Both converters are supplied with a common load. The firing angle of converter 1 is alpha 1 and alpha 1 is always less than 90 degrees. Hence the converter 1 acts as a rectifier. For positive half cycle, where the cycle varies from 0 less than t less than pi, the thyristor S1 and S2 will conduct, and for a negative half cycle means 180 to 360 degrees, that is pi to 2 pi, the thyristors S3 and S4 are conducting. In this operation, output voltage and current both are positive. So this operation is known as a forward motoring operation, and the converter works in the first quadrant. The firing angle of converter 2 is 180 minus alpha 1, that is alpha 2, and it is alpha 2 is always greater than the 90 degrees. So the converter 2 acts as an inverter. In this operation, the load current remains in the same direction, but the polarity of the output voltage is negative. Therefore, the converter works in the fourth quadrant. This operation is known as regenerative braking. For reverse rotation of the DC motor, the converter 2 acts as a rectifier and converter 2 acts as an inverter. The firing angles of converter 2, that is alpha 2, is less than 90 degrees, and the alternative voltage source supply the load. In this operation, the load current is negative and the output average voltage is also negative. Therefore, the converter 2 works in third quadrant. This operation is known as the reverse motoring. In reverse operation, the firing angle of converter 1 is less than 90 degrees and firing angle of converter is greater than 90 degrees. So in this operation, the load current is negative but the average output voltage is positive. So the converter 2 works in the second quadrant. This operation is known as the reverse regenerative braking. Here we can able to see the waveforms. First two, this is the input supply AC signal, and this is the output we are getting from converter 1. This is also converter 1 output, and here also converter 2 outputs, these two are, and the output after getting the combination of both the outputs of the converter 1 and converter 2. Let us discuss about the three-phase dual converter. Here we have a circuit diagram of three-phase dual converter. Here two three-phase converters are connected in back-to-back. In every converter configuration, there are 6 thyristors are being used. Thereby, there are existing 12 converters. The thyristor 1, which we connected left side, is acting as a rectifier. The thyristor configuration, which we connected right side, will acting as a inverter. And this is also working same as the single phase dual converter. And the dual converter having the following applications. When we want to change the speed of the DC motor or direction of this DC motor, we have to use the dual converter, and it is having the applications in reversing the DC. In industrial variable speed drives also we are going to use the dual converters.